Hello all, my paper ID is 9542. My paper title is a miniaturized circle square fractal super wideband antenna with high bandwidth dimension ratio.
Problem statement and objectives. For the past 2 decades, wireless sensor networks have become a very promising and fast developing wireless technology that has cluster of deployed nodes. It is mainly used for monitoring purpose. We need to design a miniaturized antenna because antenna occupies most of the space in the node, and we need to have an antenna that supports for very long and short range communication. Super wideband antenna is the better choice for that because it has minimum bandwidth ratio of 10 is to 1, and the antenna with the omnidirectional pattern is preferable in the case of wireless sensor networks because the nodes are scattered. And the challenge is to design smaller antenna with wider bandwidth, high gain, low cost, and high bandwidth dimension ratio. Objectives of this proposed work is to design a miniaturized fractal super wideband antenna for wireless sensor networks applications with enhanced bandwidth and larger bandwidth dimension ratio, and to analyze the antenna in both frequency domain and time domain to validate the reliable radiation properties of the proposed antenna. Contribution. In this proposed work, we have used fractal geometry etched from a circular monopole patch to enhance bandwidth and to improve the electrical characteristics of the antenna. The structural novelty of the antenna is instead of using conventional triangles, we have used concave and convex triangles which have curved edge and straight edge that produces miniaturization and leads to super wideband response with larger bandwidth dimension ratio. The proposed SWB antenna is analyzed both in frequency and time domain and found it is perform well in the both domains. Fabricated antenna shows a good agreement with electromagnetic simulated results and measured results. Antenna design and development steps. The proposed antenna is made up on FR4 substrate. A simple circular patch is the basic structure for the proposed fractal antenna. The current path is increased by increasing the patch perimeter. This is achieved by incorporating circle square fractal structure in every iteration from antenna 1 to 6. At fifth iteration, we have got broader band, and further to improve the impedance bandwidth, we have modified the conventional partial ground structure into elliptical, semi-elliptical edge and square slot on top of it. Here, this tabular column shows the iteration-wise improvement in the antenna's impedance bandwidth, and this is the iteration-wise improvement in the S11 results. This is the fabricated antenna. Results and discussion. Frequency domain analysis. The fabricated antenna is tested in anechoic chamber. The measurement setup is shown here. And this is a comparison of measured and simulated results which are in good agreement with each other. And this is the surface current distribution of the proposed antenna. The current is uniformly distributed on the patch from lower frequency to upper frequency. Here the surface current is mainly accumulated on the edges of the fractal element, which is the reason for the additional resonances and miniaturization. Here this is the radiation pattern in H plane and E plane, which shows nearly omnidirection characteristics which are desirable for our application. Time domain analysis, which is very important to predict signal distortion produced by the antenna. The proposed antenna is analyzed in time domain by means of fidelity factors and group delay analysis. Here, these are all the pulses used to predict fidelity factor, and this is the arrangement of antennas to calculate system fidelity factor and fidelity factor of the system. It shows more than 90 percentage, and here it is more than 70 percentage, which are desirable for pulsed transmission. In the case of group delay analysis, there is a least variation throughout the entire frequency band, which shows that less dispersion in the transmission, and the antenna doesn't considerably distort the input excited pulse. Performance comparison of proposed antenna with other existing work with respect to size, bandwidth dimension ratio, size reduction, etc. Here, it is observed that the proposed antenna produces a larger bandwidth dimension ratio of about 16,100, and size reduction is ranges from 9.3% to 99.1%, and as ratio bandwidth exceeds 10 is to 1, it can be used as super wideband antenna, and it is also covers UWB band. Conclusion: a circle square fractal antenna for super wideband application was successfully designed and analyzed in this proposed work. A miniaturization is achieved in fifth iteration of about 20 cross 22 square mm, and antenna produces larger impedance bandwidth ranging from 1.48 GHz to 19.98 GHz, which corresponds to bandwidth ratio of 13.5 is to 1, and produces larger bandwidth dimension ratio of 16,100, and it performs very well in frequency domain and time domain, and it is very much suitable for wireless sensor network applications. Thank you.